process control and users, we will gonna continue with the one we left off. We will repeat some of these processes because this is such an important topic in operating systems. Beyond fork, exec, and wait, there are a lot of other interfaces for interacting with processes in Unix systems. For example, the kill system call is used to send signal to a process, including directives to pause, die, and other useful imperatives. So remember the imperatives in the about face course. Imperatives is the verb or command that provides action. So other imperatives means other commands that allow us to invoke that process. In most Unix, for convenience, in most Unix shells, certain keystroke combination are configured to deliver a specific signal to the currently running process. For example, Control C sends a sigint interrupt to the process. So the sigint interrupt are actually coming from your hardware, of course, and then it sends interrupt to the process. So it's from kernel to the process, normally terminating it, and controls like Control Z sends stop, which means signal, thus pausing the process in mid execution. You can resume it later with the command like the FG built-in command found in many shells. So the resume is FG, which is built in from many of the shells. And remember, the shells came all from Unix. So this shell is just a way for you to access or to transform, used to transform again another program. The entire Signal subsystem provides a rich infrastructure to deliver external events to processes. So it delivers external events to processes, such as using your hardware like keyboard to the existing process on your PC or laptop, including ways to receive and process those signals including ways to receive and process those signal within individual processes. So not just sending it, but to configure it in ways that for receiving the process of those signal within individual processes, and ways to send signals to individual processes as well as entire process groups. So there's also a way to send signals to an individual or an entire process groups, which makes this important because again, this separation of processes allow us to virtualize our memory and makes the system easy to use. To use this form of communication, a process should use the signal system call to catch various signals. So to use all of this or for this form of communication, the signal system is called to catch various signals. So a system call, which is a signal, are used to catch these signals to be able to activate these external events that you could activate to the process, kind of like imperative control that we discussed in about face. Doing so ensures that when a particular signal is delivered to a process, it will suspend its normal execution and run a particular piece of code in response to the signal. So this system call, which is a signal, allows us to provide an execution such as running a particular code and if-else statements in response to that signal or external event. This naturally raises the question, who can send a signal to a process and who cannot? Generally, the system we use can have multiple using them at the same time. If one of these can arbitrarily send signals such as sigint to interrupt a process, likely terminating it, the usability and security of the system will be compromised. So if we allow everyone to send a signal to anyone or any process, it will compromise the security and the control and the ease of use we aspire to do. As a result, modern systems including a strong conception of the notion of user. The user, after entering a password to establish a credentials, logs to gain access to system resources. So that's where the user comes. That's why whenever you're developing codes, like in Docker, you need to log into the Docker space first, or in Firebase first. So the user may then launch one or many processes and exercise full control over them, pause them, kill them, etc. Users generally can only control their own processes. It's the job of the operating system to parcel out resources such as CPU, memory, and disk to each user and their processes to meet overall system goals. So again, users generally can only control their own processes. It's the job of the operating system to parcel out resources such as CPU, memory, and disk to each user and their processes to meet overall system goals. So it's the job of the OS or the kernel to chip out CPU, memory, and then disk access to these processes once it requests it through user mode. Once the process requests that via system call through user mode. We will continuously again refine this notion as we move forward or as we go into the details. So there are many command line tools that are useful as well. For example, using the ps command allows you to see which processes are running. Read the man pages for some useful flags to pass to ps. So this ps allows you to see the processes that running, kind of like the process list that automatically created to you by the kernel when it allocates the memory. The tool top is also quite helpful as it displays the process of the system and how much the CPU and other resources are eating up. Humorously, many times when you run it, top claims it the top resource hog. So top, used to measure CPU resources carved out, but it turns out that it is the top resource hog. So the command kill can be used to send arbitrary signal to processes, as can slightly more user-friendly kill all. So a kill, the command kill could are provided by the shell that allows you to send signal to kill that particular process. A kill all is a slightly more dangerous. Be sure to use this that carefully. If you accidentally kill your window manager, the computer sitting in front may become quite difficult to use because again, it's all started with the Windows. That's what makes the GUI become easy to use with Windows. So if you kill that GUI that makes it easier to use. So basically Unix already makes everything easier to use, such as using command line that allows you to transform it to other command line. But then you still have to remember a lot of commands, like an infinite commands. But through the generation of window, it allows you to have this screen interface. So that's where the window came from. Now, what used to be in the command is now available to you via window. That's why we have this 2D graphical user interface. So if you kill that, definitely it will definitely hard for you to type in commands because there will be no window to type in. So that's the basic idea of this. Finally, there are many different kinds of CPU meters you can use to get a quick glance understanding of the load on your system. For example, we always keep menu meters from Raging Menace software running on your Macintosh toolbars so we can see how much CPU is being utilized at any moment in time. In general, the more information about what is going on, the better. We have introduced some of the APIs dealing with Unix process creation, fork, exec, and wait. However, we have just skimmed the surface. For more detail, read Stevens and Rago, of course, particularly the chapter on process control, process relationships, and signals. There's much to extract from the wisdom therein. So we just scratch the surface of process relationships and process signal and processes. There's much more that's happening in the operating system that we would that we would have imagined, because again, this has been created or has been developed for decades now. That's why there's a lot of code inside it. But here, we're just trying to scratch its surface to maybe be able to understand its basic principles, etc. So, while our passion for the Unix process API remains strong, we should also know that such positivity is not uniform. For example, a recent paper by systems researchers from Microsoft, Boston University, and ETH in Switzerland details some problem with fork and advocates for other simpler process creation APIs such as Spawn. So the fork, the one we use to create a copy of a parent to a child, has some issues based on that system researchers. So aside the super user root, a system generally needs a user who can administer the system and is not limited in the way most users are. Such a user should be able to kill an arbitrary process, like if it's abusing the system in some way, even though that process was not started by this user. Such a user should also be able to run powerful commands such as shutdown, which unsurprisingly shuts down the system. In Unix-based systems, these abilities are given to the super user, sometimes called root. While most users can kill other user processes, the super user can. Being root is much like being Spider-Man. With great power comes great responsibility. Thus, to increase security and avoid costly mistakes, it's usually better to be a regular user. If you do need to be root, tread carefully, as of all of the destructive powers of the computing world are now at your fingertips. The fork system call is used in Unix systems to create a new process. The creator is called the parent. The newly created process is called the child. As sometimes occurs in real life, the child process is nearly identical copy of the parent. Again, that's a keyword, nearly identical copy, just like a parent and a child in the real world. The exec family of system calls allows a child to break free from its similarity to its parent and execute an entirely new program. So that's what the exec means. But there's, as we have seen, there's a lot of different ways to execute or to execute this exec VE, etc. Right? So those are systems calls are as well. It's just a different configuration. A Unix shell commonly use fork, wait, and exec to launch user commands. The separation of fork and exec enable features like input or output redirection, pipes, and other cool features. So commonly, it uses a fork, wait, and exec to launch user commands or to transform a command from a identical copy. So the separation of fork and exec enables features like input or output redirection. So the separation of fork and exec, one of the fundamental capabilities or innovation of Unix, it's allowed the redirection of input and output and pipes. So pipes came from those exec and fork as well. The vertical line, the greater than simple, and other cool features, all without changing anything about the program being run, which is amazing. Process controls is available in the form of signals, which can cause jobs to stop, continue, or even terminate. Again, process control is available in the form of signals, which can cause jobs to stop, continue, or even terminate. Again, a process control is available in the form of signals, which can cause jobs to stop, continue, or even terminate. So this is actually how we control it, which is one of the problem that we have resolved using signals or using the process. So how do we control process? One of the ways are the use of process control, which is signals. So or signal system API call. So mechanisms, limited direct executions. Oh my god. So let me just copy this. I think I got the copy wrong. There you go. So in order to virtualize the CPU, the operating system needs to somehow share the physical CPU among many jobs running seemingly at the same time. So the CPU or the operating system and the CPU must share the physical CPU among different jobs or processes. The basic idea is simple. Run one process for a little while, then run another one, and so forth. By time sharing the CPU in this manner, virtualization is achieved. So that's actually how we achieve this virtualization, by running the process, stopping it, and then running the other one. There are a few challenges, however, in building such virtualization machinery or systems or operating systems. The first is performance. How can we implement virtualization without adding excessive overhead to the system? The second is control. How can we run processes efficiently while retaining control over the CPU? So again, how can we implement virtualization without adding excessive overhead to the system? So the performance. The second is control, which solved by process control, right? But we will gonna dig deep on how the kernel actually provide control to the user. Okay, so how can we run processes efficiently while retaining control over the CPU? How can we run processes efficiently while retaining control over the CPU? So how can we run that? So yeah, how can we will gonna dictate that. So if every process has a direct access to CPU, how can we retain control over the CPU? How can it not be directly controlled by the user? We will gonna answer that here. Control is particularly important to the OS as it is in charge of resources. Without control, a process could simply run forever and take over the machine or access information that it should not be allowed to access. Obtaining high performance while maintaining control is thus one of the central challenges in building an operating system. So the first basic technique, limited direct execution. So we will gonna, from the word itself, we will gonna limit the direct execution of our user program to the CPU. So to make a program run as fast as one might expect, not surprisingly, OS developers came up with a technique which we call limited direct execution. The direct execution part of the idea is simple. Just run the program directly on the CPU. Thus, when the OS wishes to start the program running, it creates a process entry for it in a process list. So before running the program, uh, the OS, if the OS wishes that, it creates a process entry first in a process list, and it allocates some memory for it first, obviously, in the back, in the front end, right? It loads it in the front end, loads the program code. So only that's the only time it loads the program code when there's an actually memory allocated for it. And it loads that coming from the disk, locates its entry point like the main routine or something similar, jumps to it and start running the user code. So just like what we've discussed in the previous chapter, it runs it starts running the user code. So the user code starts with main, right? So it's already loaded into the virtual memory of that process. So we create the per process structure for that, and we allocate a stock memory. So this stock memory will run the code. Okay, this stock forms last in first out. So it's a LIFO structure because that will allow us to go back to the previously running code. Let's say the code, for example, will execute or delete some file. So that requires an input or output. So while the kernel in the back end are running an input or output, our code will stop at there. So that stop will transfer that register, or where the user or the program counter, what we call program counter, where the user code stops, and then save it as such to a kernel stock, So while the kernel are doing the deletion in the file system or unmapping the node, the code stops. So in the kernel, we were able to drop into the kernel. So once we are able to drop into the kernel, it will execute that IO first before it return the trap back into the user for it to get back to the user mode. So that's actually how we run the program directly on the CPU. So thus when OS wish to, it creates process entry 4 and starts the running the user code. So there's an intricate details on how the Unix system or operating system actually runs the code. Now figure 6.1 shows the basic direct execution protocol without any limits yet. So it doesn't incorporate the limited direct execution we're talking about, using a normal call and returns to jump to the program's name and later back into the kernel. So these are the simple without limited execution yet. So we will gonna refine this notion. So OS, it first create an entry for process list, so it can track this. It allocate memory for the process or for the program. For the program, that's the right word, because the program is not a process yet unless there's a memory, right? So load program into memory, it becomes a process. It's set up stock with arg/arg, like the code we have in our .c earlier. It clears registers, execute call to the main. So it set up that stocks, and then it clears the registers, and then it execute that code. Now this code, this program, it runs the program execute return from main. So it will return from main, and then it will free the memory of the process. So the OS are the one responsible for clearing the memory of process, since it is the one that allocates this virtual space from it. Whether you've done a fork or exec that transform a child to another process, it doesn't matter. It free that memory, or it kills that. So remove from process list. It also remove it from process list. So that's the direct execution protocol without limits. Sounds simple? No. But this approach gives rise to a few problems in our quest to virtualize the CPU. The first is simple. If we just run a program, how can the OS make sure the program doesn't do anything that we don't want it to do while still running it efficiently? The second, when we're running a process, how does the operating system stop it from running and switch to another process, thus implementing the time sharing required to virtualize the CPU? So the first problem is to make sure that a process doesn't do anything we want to do. So that can be solved by separating user mode and then kernel mode. And the second problem, when we're running a process, how does the operating system stop it from running and switch to another process? So we will implement what we call trap. So that's how we transform from user mode to kernel mode. We will gonna also implement the context switch. So this is what allows us to virtualize the CPU. So problem number 1, restricted operations. Direct execution has the obvious advantage of being fast. The program runs natively on the hardware CPU and thus execute as quickly as one would expect. But running on the CPU introduces a problem. What if the process wishes to perform some kind of restricted operation, such as issuing an I/O request to a disk or gaining access to more system resources such as CPU or memory? So that's where trapping and the kernel mode comes in. You may wonder why a call to a system call such as open or read looks exactly like a typical procedure call in C. That is, if it looks just like a procedure call, how does the system know it's a system call? So if it looks like a procedure call in C, how does it know that it's a system call and do all the right stuff? So this is where the trap these are written in assembly, so it's not written in C. That's the answer. So the simple reason, it's a procedure call, but hidden inside that procedure call is the famous trap instructions. So that trap instructions is actually a assembly code. It's not written in C. It's a special instruction. That's why it's called trap instruction. It's used to trap into the kernel that requires privilege mode, such as an I/O, memory, or tapping into CPU. More specifically, when you call open, for example, you are executing a procedure call into the C library. Therein, whether for open or any other system calls provided, the library uses an agreed upon calling convention with the kernel. So in this open, first you tap into this open library call, but it's just a C library call wrapped into assembly code that is agreed upon calling convention with the kernel to put the arguments to open in well-known location, like on the stock or in specific register. Puts the system call number into a well-known location as well, again under the stock or register, and then executes the aforementioned trap instruction. The code in the library after the trap unpacks return values and returns control to the program. So the code in the library after the trap unpacks the return values and returns control to the program that issued the system call. So since it's an assembly code, it will return whether it's successful, like 0. So let's say your code, like if r rocks or equals to 0, and then once that kernel returns the 0 on your code will read it as successful, and that therefore will return the appropriate code or command that you execute it. Thus, the parts of the library that make system calls are hand-coded in assembly. So the parts of the C library that make system call are hand coded in assembly. So again, it's hand coded in assembly. So it put that as well in a well-known location, of course, like a virtual space. So the kernel carved out, to make it more detailed, the kernel actually carved out a kernel per process stack. So that kernel per process stack actually save the program counter where the code stops, and then execute that trap or written in assembly code trap handler such as open. And then when it returns the values, it returns as well the stock here and the registers for the code to continue executing, as they need to carefully follow conventions in order to process arguments and return values correctly. The reason why this trap is written in assembly code is because they need to carefully follow conventions in order to process arguments and return values correctly. So to process the arguments, since you're tapping into the CPU, disk and memory, you need to be more direct. That's where the assembly code came in. We are more detailed in the instruction we are giving to the computer, as well as execute the hardware specific trap instruction. So as well to execute the hardware specific trap instruction. So the reason for that as well is to be able to contact the kernel text, which has the kernel instruction that will allow to that will be of course compiled to assembly, and then we're gonna talk to the CPU. So that communication as well are important. That's why it's written in assembly code, and then it will return it via kernel stack, and the result of that execution or that logic instruction to the CPU. And now you know why you personally don't have to write assembly code to trap into an OS. So you don't need to write a assembly code because there's a trap instructions available, that you only need to use a system call like open for a file system. Somebody has already written that assembly for you. One approach would simply be to let any process do whatever it wants in terms of I/O and other related operations. However, doing so would prevent the instruction of many kinds of systems that are desirable. For example, if you wish to build a file system that checks permission before granting access to a file, we can simply let any user process issue IOs. So let's say your folder, like in your Windows, you decide to protect that. You put a password. So if you just let any program access into the file system or trapping into that kernel part without actually providing this kernel stack or trap instruction in assembly, you wouldn't be able to secure that file. Therefore, you introduce a lot of problems if the user doesn't want that. So we don't want our system to be like that, because we're designing for all of those edge cases. So if we did, a process could simply read or write the entire disk, and thus all protection would be lost. So if indeed if there's a bug onto the process, it could simply write and delete all of the files, and all of the data will be lost. So that's the issue with this operating system. That's why it wouldn't work. That's why we have a lot of bugs in the earlier operating system. Thus, the approach we take is to introduce a new processor mode known as user mode. Code that runs in user mode is restricted in what it can do. For example, when running in user mode, a process can issue I/O request. Doing so would result in the processor raising an exception. So if you're in user mode and you request an I/O, and then you didn't follow the rules of trapping into that only way for you, such as a trap instructions or communicating via assembly, which is a secure way designed by the modern operating system for you to communicate to the hardware, it will return an exception or an error. the OS would then likely kill that process, and then you might the OS may decide to exit your program, which is more bad case. So in contrast, the user mode is kernel mode, which the operating system or kernel runs in. In this mode, code that runs can do what it's like, including privileged operations such as issuing I/O requests and executing all types of restricted instructions. So this kernel mode is actually the one we are doing whenever we're deleting file. Now, if we wants to secure or protect our file, we can do so because we have this another mode in our operating system, such as kernel mode. Let's say we want to restrict our file so that we want to save password so that not any process can access this. We can do so because we have this kernel mode, so we can configure it better. In contrast to user mode, is kernel mode, just operating mode, which the operations including all restricted. We are still left with a challenge, however. What should the user process do when it wishes to perform some kind of privileged operation, such as reading from disk? To enable this, virtually all modern hardware provides the ability for user program to perform a system call. So this is actually how we solve the problem when it wish to perform like what I've said, we're using a trap instruction or system call, and then that system call are wrapped in a trap instruction that allows us to access the assembly code and tap into the kernel text that allows us to securely communicate and do those secure operations. So that's our where a system call came from. Pioneered on ancient machines such as the Atlas, system calls allows the kernel to carefully expose certain key pieces of functionality to user program, such as accessing the file system, creating and destroying process. So even creating and destroying process are allowed by this system call. So the signal that we have discussed, not just the I/O but also the signal that used to kill and destroy process are enabled by these trap instructions, destroying process, etc. So this is also related to the context switching that we have discussed before. Communicating with other processes as well and allocating more memory. So those are one of the higher level tasks. Communicating with other process, allocating more memory, talking to the CPU directly. Most operating systems provide a few hundred calls. See the POSIX standard for details. Early Unix system exposed a more concise subset of around 20 calls. Tip: use protected control transfer. The hardware assists the OS by providing different modes of execution in user mode. So the hardware assists the OS by providing different modes of execution in user mode. So even in user mode, the hardware already provides you different modes of execution or call that you can provide. Applications do not have full access to hardware resources. So it doesn't have full access to hardware resources. Maybe you're not allowed to use any input or output action or any networking side. You're only allowed to access some of the hardware such as CPU. In kernel mode, the OS has access to the full resources of the machine. Special instructions to tap into the kernel and return from trap back to user mode programs are also provided. So these are the key that makes us this password in your file system, so that you achieve the security. You don't all of the users could not just access it because you provided this trap into the kernel and return from trap back to user mode programs to get back from kernel to user mode, as well as instructions that allow the OS to tell the hardware where the trap table resides in memory. There's also an instruction that allows the OS to tell the hardware where the trap table resides in memory. So that trap table will tell your operating system whenever there's some unhandled edge cases. For example, in boot time, you have this the user accidentally press escape or anything malicious, or the disk suddenly did not work at boot time, that would could uh, destroy the system. The operating system prepare for that using this trap table. So these are written in assembly as well. So these are the high level instructions that keep or make your system secure from those uh, edge cases. Now, to execute a system call, a program must execute a special trap instruction. So every system call, our program actually is by default in a user program, and every system call, it actually execute a trap instruction, not in some system call, in every system call, to be able for us to communicate with the hardware. So every system call, not just some. So this instruction simultaneously jumps into the kernel and raises the privilege level to kernel mode. Once in the kernel, the system can now perform whatever privilege operations are needed, if allows, and thus do the required work for the calling process. So that calling process that has a virtual memory will call this, will trap into the kernel, and if the kernel needs some hardware to perform that, such as CPU, it will save the kernel stock, the program counter, the register it needed to go back onto that last state of the process, that allows it to return values once it succeeded doing the operation. So that's allow us to run programs concurrently, because this operating system switch from user mode to kernel mode when it's done a system call. So yeah, the hardware needs a bit sorry, this instruction simultaneously jump in the kernel and raises the privilege level to kernel mode. Once in the kernel, the system can now perform whatever privilege operations are needed, if allowed, and thus do the required work for the calling process. So the kernel will gonna do the required work for the calling process, and that calling process will stop or will gonna show loading depending on how it is coded by the developer. If it does not show loading, therefore it provides a bad UI design, because you should always provide loading graphical interface whenever you're waiting for some operations in the back end, and then return back to you. When finished, the OS calls a special return from trap instruction. So since it's assembly code that talks to the kernel text, the kernel use a return from trap instructions that allows this execution to return values, the kernel text, which is the return from trap instruction, as well as it returns as well the kernel stock per process that allows the process to go back to its previous state. And also for the kernel stock process, it only it has the register, but it's not the actual register of the CPU. It's just a representation of the memory of the process where it left out, so that the program could go back to the program counter where it previously left off, which, as you might expect, returns into the calling user program while simultaneously reducing the privilege level back to user mode. The hardware needs to be a bit careful when executing a trap, in that it must make sure to save enough of the caller's register in order to be able to return correctly when the OS issues the return from trap instruction. So this saving of a caller's register is the kernel per process stock that allows it to return correctly when the OS issues the return from trap instructions. On x86, for example, the processor will push the program counter, flags, and a few other registers, which is the representation of the registers of the CPU where it left off. The program counter is the code where it left off, and a few other registers onto a per process kernel stack. The return from trap will pop these values of the stack. So the return from from trap is a code from a kernel, or is a kernel rather assembly code that allows it to pop and then return to the user mode. So the return from trap is what actually return this per process kernel stack to the user. These values of the stack and resume execution of the user mode program. So see the Intel system manuals for details. Other hardware systems use different conventions, but the basic concepts are similar across platforms. There is one important detail left out of this discussion. How does the trap know which code to run inside the OS? That's a good question. Clearly, the calling process can specify an address to jump. So the calling process should not be able to specify an address to jump as you would when making a procedure call. If it can do that, it can compromise the security of the hardware, because OS is the one managing it. It's the only one managing it. Therefore, you have to do the trap instructions or system call whenever you want to do something. Doing so would allow programs to jump anywhere into the kernel, which clearly is a very bad idea. Thus, the kernel must carefully control what code executes upon a trap. So the kernel must carefully control. So it controls what can be executed upon a trap. That's why it's a limited direct control. The kernel control what you could execute on that system call. It doesn't allow you any to do any thing that will compromise that operating system or your PC. So the kernel does so by setting up a trap table at boot time. So this is how it controls what code executes upon a trap. So the kernel does so by setting up a trap table at a boot time. When the machine boots up, it does so in privileged kernel mode, and thus is free to configure machine hardware as need be. So when you start booting up, it does so in privileged mode or kernel mode, and thus it can configure the machine hardware on whatever it like. One of the first things the OS does is to tell the hardware what code to run when certain exceptional events occur. One of the things that it does is to tell the hardware what code to run. So it prefers the edge cases when certain exceptional events occur. For example, what code should run when a hard disk interrupt takes place. So what will you run if the hard disk interrupts take place? When a keyboard interrupt occurs, or when a program makes a system call. A keyboard interrupt or a program makes a system call. The OS informs the hardware of the location of these trap handlers. So the OS will inform the hardware of the locations of these trap handlers. So these are called trap handlers because it handled the trap, right? Usually with some kind of special instruction. So there's a special instruction in it that allows you not to control what you can execute on the machine. So these trap handlers are the special instruction that allows us to control what can be executed or limitedly to our machine. And at boot time, it set up this trap table. So this is how the OS magic came from. Once the hardware is informed, it remembers the location of these handlers until the machine is next rebooted. So since it Thus that in the boot time, this page table, the hardware is now informed that it is limited in what it can do, to make sure that those trap handlers will not be executed because it's a trap. It could in about phase course, it could entirely disrupt the functionality of the system. So it will remember the machine, or the hardware will gonna help the OS to remember that until the next boot, which will save again, or it will set up a page table again. And thus the hardware knows what to do, what code to jump to when system calls and other exceptional events take place. So that system calls is actually part of the exceptions that hardware would provide to the user mode for it to be able to access those machines, or hardware.